Hello everyone. In this video, we are going to talk about the Mann-Whitney U-test, also known as the Wilcoxon rank sum test. And it's a non-parametric test. We're going to talk about what is a non-parametric test. If you remember, a few videos ago that I published, it was on t-test in statistics. And we learned that in t-test, one of the major assumptions, one of the first assumptions is that your data is approximately normally distributed. Okay, and especially when the sample size is small, it is very important that you have that normal assumption. And I said if it's not, then we can use this Wilcoxon sign rank test or Mann-Whitney U-test. So that is the time now. Let's talk about it, that if your data is not necessarily normally distributed, can you still compare two different groups together? Can you still perform a t-test? And the answer is yes. But this time we use this Mann-Whitney U-test. Now you might say, what is non-parametric test? Non-parametric means the population, the underlying population of the samples does not depend on any parameters. You know, when we say the distribution is normal, in the normal distribution, if you remember, the PDF of it was basically 1 over square root of 2 pi sigma squared e to the negative x minus mu over sigma, the whole thing squared, right? We had this in one of these previous videos that I talked about the z-score and t-score and everything, right? Look at it, that's right here. And now there was a 2 sigma, not sigma. So my bad, here there is a 2 sigma. Sometimes I forget that. Okay, now that one is squared over 2 sigma squared. So if you want to write it properly, you have to write it like this. Okay, so now you see clearly here, this distribution does depend on two parameters, mu and sigma. Or if you looked at the t distribution, student t distribution, remember it was depending on this parameter nu, which was the degree of freedom. But if we don't know anything about the underlying distribution and we cannot give it a function like this with some parameters, then we have to use tests that are non-parametric, or the distribution underlying them does not depend on any parameters. And this is mostly works based on the ranks. So these non-parametric tests, the most important thing about them is you rank the data when you sort them from the smallest to the largest, or vice versa. They typically work based on the rank, and based on the ranks of the data in the two samples, we can compare them, okay? So that's what we also going to see in the next video, where we talk about the Kruskal-Wallis test, which is a non-parametric version of ANOVA. Then we're going to see again, we're going to use the ranks. So that rank is very, very common in non-parametric tests. Okay, so now what are the assumptions for Mann-Whitney U-test is, first of all, the data in the samples are independent from each other. The sampling is done randomly, and the data could be sorted or could be ranked. So the data should be ordinal or continuous data. Okay, if the data is something like categorical data that is, I don't know, like fall and spring and summer and winter, and you cannot really rank them based on something, then this method is not useful. Okay, so working on categorical data is a different story, and I can make a video about that. So here we assume the data could be ranked. Now, the null hypothesis, if we use a two-tailed t-test, which is the most common version of this test, is that the two samples are coming from the same distribution. Okay, no shifts here. But instead of saying the shifts in the means, remember in the past we said that mu of sample A is the same as mu of sample, or in this case not really mu, x bar, or yeah, it is, because they are coming from the same distributions. So mu of distribution that sample A comes from is the same as mu of the distribution of the one that sample B is coming from. So this was it. Now in this case, we are not going to say that, and the alternative is that they are not equal and there is a shift in the average. Okay, now this time instead of saying shift in the average, we have to say shift in the medians. Why? Again, because median is based on the rank, and you know that when we sort the data from the smallest to the largest, the middle data is called the median. So here we use the middle of rank data, which is median, for comparison, not the average of the data, okay? So medians are going to be shifted or not going to be shifted in the null hypothesis or alternative one. In one-tail U-test, that is less common, there are two versions. Either we say the left-tailed alternative or the right-tail alternative. You might say, what was the null hypothesis? The null hypothesis is that, again, the two medians have no shift. They are equal. But now, if the test that we are doing is a left tail, the alternative hypothesis of that, instead of them not being equal, is that median of A is less than median of B. Okay, and if it's a right-tailed test, the alternative is that median of A is bigger than median of B. Here, this is like median of A equal to B. That is the null hypothesis for both one-tailed and two-tailed. But the alternative here is that for two-tailed, that the median of A is not equal to median of B, but in the one-tailed, it's either one bigger than the other or the other one. So A bigger than B or B bigger than A. Okay? So these are the hypotheses for one-tailed and two-tailed. Now, how do you perform this? So as with other tests, you need to get a statistics value and a critical value and compare them. So here we need U statistics and U critical. To get the U statistics, this one here, we need to get U1 and U2, the U, sum of the ranks, or U value, not just sum of the ranks, this is sum of the ranks, U value for group 1 or sample 1, U value for group 2, and then the minimum of these two is going to be my U statistics. Now, how do I get U1 and U2? So both of them have a similar term in them, N1, N2 plus N1 times N1 plus 1 over 2. The second one, the product term is the same. This term is just calculated using N2. And then minus sum of the ranks of the data in group 1 minus sum of the ranks in group 2, okay? So once we calculate these, U1 and U2, from the minimum of them, we calculate U statistics. And you might say, what if one data from group 1 and one data from group 2 are identical? So when you want to sort them, one of them, although they both the same value, but when we rank them, when we sort them, one of them has to be called data number, for instance, 10. The other one should be called data number 11. So what would you do? Because they are the same data, you average those two ranks for the ties and give each one of them the same thing. What does that mean? So let me go through an example. So let's say here you have two samples that are showing the effects of, they are acquired to investigate the effects of a specific fertilizer on the growth of a plant, the height of a plant in centimeters after 4 weeks. So when they use fertilizer A, these are the height of the plants. These are the 5 samples that they got. And when they use fertilizer B, these are the 5 data that they got. These are the 5 heights. So now if I get these 10 data values and sort them from the smallest, which is 10, to the largest, which is 22, this is what I will get. 10 is my smallest data, rank 1, all the way to 22, which is my largest data, that's rank 10. Good? Now, if it happened to be that this group A, instead of this 14, it was also 10. So you see they both share a 10. Then what? then there is a 10 for group B, and there is a 10 for group A. So one of them is called rank 1, one of them is called rank 2, and that's not correct to give one of them rank 1, one of them rank 2, because they are the same number. So I take the average of these two, and instead I give each one of them 1.5, which is the average of them. Okay, so this is how you handle basically identical data in the two groups, or handle ties, basically use average of the ranks. So in this case, what do we do? In this case, N1 and N2, the number of data points in each team is 5. So N1 and N2 are both 5 in this case. Then we calculate also NA times NA plus 1 over 2 and NB times NB plus 2. Okay, for both of them, the number is again the same. Then we need to sum the ranks in group A and sum the ranks in group B. And then we are going to subtract them from the rest of the numbers. So what is this going to be? This is going to be 25. This is also the same. That is 5 times 6 divided by 2, so that is 15. So sum of these two for both of the groups is 40. Okay, there is a 20, 5, and there is a 15. And then what? Then we go and sum the ranks in groups A and B. So here, what is sum of the ranks in group A? So here we know which one of these data belongs to which group. So whatever rank it has, we allocate it to that. So when I want sum of the ranks in group A, I look at where the A data are and look at the ranks. So I have a 4, a 5, a 6, a 7, and a 9. And if I add these numbers together, my total rank for group A is 31. So the number UA is going to be 25 plus 15 minus 31, and that number is 9. So U of A is going to be equal to 9. This is the critical number for group A. Then I do a similar thing for group B. So for group B, again, is 25 plus 15 minus. So now look at group B. So the numbers are 1, 2, 3, 8, and 10. And if I add these numbers, that's minus 24. So you are going to get 16. So U of B is 16, U of A is 9, and the minimum of them is 9. So your U stat, in this case, it's going to be equal to 9. Now you might say, what is this formula? This doesn't look like the same thing you did up there. Yes. You can show that if you have one of the numbers, UA, UB, instead of going through this formula, you can show that UA plus UB is always equal to NA times NB, the number of data in both of them. So if one of them turn out to be 9, some of them in this case is 25, so the other one has to be 16. Okay, so this formula always applies, that sum of the two critical U's for the two groups is equal to the product of their numbers, the number of data in each. Okay, so here, instead of doing this, we did this shortcut and we found it. Okay, so my U stat is 9 in this case. Now I need to find a U critical and compare it against. So here we have what we call U tables. This is an example of a U table. Now U tables are typically large. So this one that you see here is just a snapshot of a U table. U tables are really, really large. Why is that? Because when you want to read a U table, there are 3 numbers that you need. You need a significance level alpha, as well as the 2 degrees of freedom, N1 and N2, or NA and NB. They are the same thing. So if you look here, here you have alpha for a 2-tailed test. Here you have alpha for a 1-tailed test, which is half of that. And then we have to have lots of combinations of N1 and N2. So for N1 of 3, there are all of these numbers for N2. Then for N1 of 4, again, there are all of these numbers for N2. And then there is a similar thing, right? Because there are tons and tons of combinations. And here, now at the end of the day, once you have N1, N2, and alpha, you can go ahead and read some critical U value. If you want to do that in MATLAB, the command to do it, which directly gives you P instead, is the command rank sum. So the command rank sum does a great job in MATLAB. It does not even need to go and read the U table. What it directly gives you back is the P value. And all you need to pass to it is the data in group A and the data in group B, and tell it whether the tail is a both or a left or a right. You don't even need to give it alpha. Why? Because once it gives you back the p-value, now you can compare your p-value against alpha. If it's less than alpha, you reject the null hypothesis. If it's bigger than alpha, you don't reject the null hypothesis. If you want to work with U critical from these tables, if your U stat is less than or equal U critical, you reject it. If it's bigger than U critical, you fail to reject it. So you can either both work on U critical and U stat, or work with p-value and alpha. Both of them are good. And one thing that I want you to pay attention to is that the way that we do the hypothesis testing for U-test is kind of the opposite of Z, T, or F. If you look at Z, T, or F, we rejected the null hypothesis when my stat value was bigger than the critical value. Whether it was T or it was F or it was Z or anything, right? In order to reject it, we had to have our stat value bigger than critical to reject it. This time it's the opposite. In order to reject it, it has to be less than the critical to reject it. Okay, so please pay attention to this difference here. So in this case, if I go ahead and read off of the U tables with 5 and 5, because my N1 and N2 are 5 and 0.05, if I go ahead and read the U values, I found it is only 2. So critical is 2, my stat is 9. And 9 is, guess what? Bigger than 2. And in previous cases, as I said, T, Z, and F, that means rejection. In this case, bigger means no rejection. So you fail to reject, and fail to reject means there is no significant difference. Fail to reject is kind of like accept, and accept is what? What was your null hypothesis? It was that the medians are the same. So here I have to accept that the median height or growth of plants under fertilizer B is no different than fertilizer A. So this fertilizer was not really as big, was not as bad as they say better than A, or A was not much better than B. They are kind of doing the same job, not much of a difference. Okay? Now in this case, clearly we did not have all the data for these different fertilizers. We don't know if the distribution of these heights after 4 weeks in these plants under different fertilizer, is that distribution normal or not? We don't have enough data to make such a conclusion. Since we don't have that assumption, and the number of data in my samples are small, 5 and 5, it's not more than 30 or something. The samples are small. I don't know anything about normality of the data. To be safe, instead of a t-test, I would definitely use a what? I would use a u-test. So hopefully this video was useful to you. I'll see you in the next video.